When we consider the different kinds of data that a language can support, then there's atomic data, which includes numbers, booleans, and so on. There's compound data, which includes pairs and records, values that compose other values. But then there's also variants. And by variants, I mean the kinds of types we create with defined type, where a grade can either be a percent or a pass-fail. And these different variants can in fact have different types inside of them. And a chain could be an end or a link, where the next tree itself is a chain. So not only do we have different kinds of types, but we can also have recursive types, where one of the variants, one or more of the variants, refers one or more times back to the type that we're defining. Lists, as we've seen, has this structure inside of it, where an int list is either empty or cons of a number onto an int list. In general, our defined types allow any number of variants and any number of fields within a given variant. But as usual, we're going to simplify this down to make it as small or simple as possible. So we're going to consider defined types with two variants, where each variant just has one value inside. We can encode these kinds of simple variants. Some of them we can encode just using pairs with a tag 0 or 1 to indicate which of the variants we're in. For example, percent would pair a number with 0, where pass-fail would return a boolean with 1. But we can't have, in our type system, we can't mix pairs of numbers with pairs of booleans. So what we really have to do is pair 0 with a pair that contains a dummy boolean and an actual number, or 1 with a pair that contains a number and a dummy number and an actual boolean. And then if we wanted to write the pass function that takes either kind of grade, then it can check that type. And if it's a percent style grade, then it can pull the first out of the pair and compare that to a number. And if it's a pass-fail kind of grade, then it can just pull the second part out. So we see here how certain kinds of variants can be encoded just using functions and pairs. It does fit into our type system. And there's a drawback that we have to make up dummy numbers and dummy integers and so on, but you can always make this work out. When we try this encoding for a recursive data type, then we run into trouble. In this example, this is the chain example, where end and link are supposed to both return chains, and link takes a chain to return a chain. So what is the type of a chain? Clearly, since end takes a number and returns a pair, using the 0 tag to say we're end cased, then a chain is a num cross num. And so that means link takes a num cross num, which means this R is a num cross num, and it pairs a 1 with that chain, a 1 saying we're in the link case. But that means if R is a num cross num and we pair it with 1, then the result over here is a num cross num cross num. But now that means that we can't take the result of link and pass it back into link. And the problem here is that we need this type and this type to be the same, and if we try to make them the same, the types don't work out, so we're stuck with this encoding when we try to make recursive things. And this should feel familiar. It failed for much the same reason that our encoding of recursive functions didn't work. And if we try to do the list example, integer list example, we run into the same problem here. There's nothing that'll go in place of this ... There's no type that you can write to make the type checker happy. So what we have to do to make the type checker happy is add a notion of variance and variant dispatch into the language. So just like we have defined type and PLAI typed, we're going to introduce let typed, a local binding variant of defined type, and the usual type case form. So here I'm letting the type numList be a new type with variants empty and cons, where empty just has a dummy number inside of it, and cons pairs a number with another numList. Okay, and then here's a use of type case in the simplified form, where we type case a numList L. We have either the empty or cons case. Since we're writing the recursive length function, we return 0 for the empty case, and 1 plus the length of the second part of the pair inside of a cons for the cons case. So you can see we can write recursive length because we have letrec, but we need a recursive num data type, and that requires let type and type case. So our new grammar is going to look like this. We'll keep letrec, but we'll add in let type and type case which are simplified compared to PLAI typed, and that there's always only two variants, and we don't bother naming the fields inside of a variant. We just give the field a type. And so when we do a type case, we always have two variants, each with a single field that we locally bind for use in this expression. Not only is our expression grammar extended, but our type grammar has to be extended also, because we have to be able to use a name that we've defined as a type.